Welcome. This is the end-of-project presentation for REALISATION-SAND-AI, a 12-month applied research project at the intersection of multi-physics simulation, deep learning, and reinforcement learning control. The project was carried out at Kyamos in Nicosia, Cyprus, and it is funded by the EU Recovery and Resilience Facility, Next Generation EU, and by the Republic of Cyprus through the Research and Innovation Foundation, under the Repower EU component of the Cyprus Recovery and Resilience Plan. Over the next 40 minutes, I will walk you through what we set out to do, what we built, what we found, and what we did not solve, including the remaining open questions we have flagged for follow-on work. Here is the problem the project exists to solve. Cyprus has more photovoltaic generation than its low-voltage feeders can absorb, and the gap is widening under EU climate targets. On sunny days, PV surplus exceeds local demand. Current flows back through the feeder, raising bus voltages above the 1.05 per unit compliance limit and pushing some lines past 100% of their rated capacity. The distribution system operator's standard response is to curtail PV generation, disconnect it, discard it, to protect the network. In our evaluation scenarios, this curtailment reaches about 100 kilowatt-hours per 2-hour episode on a 100-household feeder. That is wasted clean energy. Distributed sand thermal storage at the household level offers a complementary path. Absorb the surplus as heat, then use it to displace fossil fuel winter heating. But deciding when and where to charge storage safely on a real feeder, under stochastic PV generation and stochastic demand, is a hard sequential decision problem. That is what this project solves. Our approach combines 3 technical pillars into one integrated smart grid digital twin. First, physics. A GPU-accelerated Lattice Boltzmann thermal solver with a multiple relaxation time collision operator running on CUDA with MPI. We use it to simulate the thermal behavior of sand storage cells in 3 dimensions at a grid resolution of 96 cubed. That is 884,000 cells per scenario, and we executed a campaign of 43 such scenarios, completing the whole campaign in about 12 minutes on our V100 cluster. Second, artificial intelligence. We trained 2 neural network surrogates on the simulation data, a 2D UNet for planar thermal fields, and a 3D volumetric model we call TUNet. The 3D model delivers sub-Kelvin accuracy at millisecond latency, for orders of magnitude faster than running the direct simulation. Third, reinforcement learning control. An Impala V-Trace dispatcher chooses, at each 1-minute control step, from a 64-action joint policy space. It is wrapped in a 2-layer deterministic safety shield. We applied the whole stack to a real 308-bus Cypriot low-voltage feeder, reconstructed from utility drawings. Before we go into how we built the system, here are the 3 numbers you will take away from this talk. Greater than 70%. The reduction in peak internal temperature rise when we compare a 9-pipe distributed heater geometry to a single central pipe at the same total power. This is the design-relevant finding from the thermal campaign, and we return to it on slide 13. 0.636 Kelvin, the mean absolute error of our 3D volumetric AI surrogate, TUNet, measured with 8-way test time augmentation on an offline benchmark. We return to the AI section on slides 14 through 17. 29.9%, the mean winter PV curtailment reduction achieved by the reinforcement learning dispatcher in scenario S1, averaged across 10 independent training seeds against a matched PV-only baseline. This is the grid integration result, and we revisit it on slide 22. Keep these 3 in mind. Now let us see how we got there. For context, the project was executed against a 5-work package plan over 12 months, from April 2025 to March 2026. WP1 was project management and reporting, covering the kickoff minutes, the midterm progress report, and this end-of-project report. WP2 was dissemination, communication, and exploitation, the 2 submitted manuscripts, this presentation, the promotional material, and the IPR and commercialization deliverables. WP3 was the sand storage thermal model and the grid power flow simulation, including the GUI. WP4 was AI dataset generation and thermal prediction. WP5 was system integration and demonstration. Headline numbers: 47.6 total person months across 5 work packages. 3.6 new full-time equivalent positions created at Kyamos during the project. And Technology Readiness Level 6, a validated integrated demonstrator in a relevant operational environment, with Technology Readiness Level 7 to Technology Readiness Level 9 activities planned as post-project follow-on. Part 1. Thermal Physics of Sand Storage. Over the next 7 slides, I will walk through the solver we built, how we validated it, how we used it on the 43 scenario campaign, and the single most design-relevant finding we surfaced, the distributed heater result. Why Lattice Boltzmann for a thermal storage problem? 3 reasons. The update rule is explicit and strictly local, which maps beautifully onto GPU architectures and gives near-ideal parallel scaling. The multiple relaxation time collision operator handles high conductivity contrasts with good numerical stability, and we have a 10,000 to 1 contrast between heater copper alloy and insulation. And the same framework is reusable across flow, conduction, and coupled problems in our multiphysics stack. For sand storage, every cell is treated as solid, so the flow branch is disabled, and the transport reduces to pure conduction with volumetric sources in the heater cells. The per-material relaxation times span 3 orders of magnitude. Sand at tau 0.8 sets the target regime. The insulation and steel are well-behaved. The heater pipes run at tau about 151, very large, a regime where most practitioners would be nervous, but we observed empirical stability across every scenario in the campaign, with no special treatment. I will come back to the honesty around this in the next slide. Here is how we validated the solver. For independent benchmark problems, chosen to exercise different parts of the code. The Poiseuille channel tests the flow branch and wall boundary conditions. The thermal source 1D benchmark exercises diffusion, the volumetric source term, and the MPI halo exchange simultaneously. The 2 heated cavity benchmarks test pure conduction and coupled buoyancy. All 4 benchmarks pass with residuals well below standard thresholds, new errors of 0.008% and 0.4% on the cavity problems. Now the honesty callout. In earlier project documentation, we reported a 0.01% energy conservation residual as a 5th benchmark. Under a proper audit, we determined that figure was a temperature sum source consistency check, not a full enthalpy balance. The actual full domain enthalpy ratio for the adiabatic nominal charging case, stored energy divided by injected energy, is approximately 0.416 at 96 cubed resolution. The solver is not enthalpy conservative. Comparative design trends and scenario-level thermal fields remain valid within the pure conduction scope, but absolute stored energy magnitudes need to be read with that ratio in mind. An enthalpy conservative reformulation is identified as Tier 1 future work in Paper 1. With a validated solver, we ran a campaign of 43 three-dimensional scenarios on our V100 cluster. Each scenario resolves 884,736 cells at 96 cubed resolution, runs 5,000 Lattice Boltzmann steps, corresponding to approximately 16 hours of physical charging time, and takes 33 seconds of wall clock on AV100. The whole campaign completes in about 12 minutes on 2 nodes with CUDA-aware MPI. The nominal charging case, T01 shown here, has a single central heater pipe driving the sand. Note how the material layout organizes the temperature distribution. The heater supplies the central source, the sand conducts outward, and the shell insulation system moderates the external boundary. We will use this same geometry as the reference against which the distributed heater configurations are compared. Here is what charging looks like as a time sequence. This is the amplified charging scenario T03 at 5 times nominal power, shown on the XY midplane at several time points. 2 things to notice. First, the thermal front expands monotonically outward. That is classical diffusion-dominated transport, exactly what we expect in an all-solid sand domain. Second, The front retains a nested concentric structure throughout. Cylindrical symmetry is preserved. Higher source strength pushes the front outward faster, but it does not change the shape of the thermal field. This is the visual signature of good conduction behavior. A conduction-dominated field that stays symmetric under amplified source strength is the foundation for confident AI surrogate training, which is what comes in Part 2. Two more findings from the thermal campaign. Discharge behavior. When the storage cell is initialized from a pre-charged Gaussian state with no active heating, and the outer boundary is at ambient, the field cools outside in. The outer region relaxes toward ambient first, while the warm core persists at the center because stored heat must diffuse through the sand and the structural layers before it can leave the system. The persistence of that warm core is our indicator of residual internal thermal energy during the discharge window. Here is a finding that is not obvious. 3 external skin surface temperature fields for charging, discharge, and 9-pipe distributed charging on matched cube views. The charging case carries a localized rise at the pipe footprint. The discharge case, however, has returned essentially to ambient on the outside while the interior still holds usable stored energy. And the 9-pipe case has a much flatter external footprint than the single-pipe case. The design implication in the callout below, external thermography alone cannot estimate residual stored energy. Storage cells need internal instrumentation or digital twin reconstruction to do state of charge estimation reliably. This is important for anyone thinking about real deployment. We now get to what I consider the most design-relevant finding of the thermal campaign. On the left is T01, the single central pipe. On the right is T42, a 3x3 distributed array of 9 pipes. Same color scale, same cutaway view, same total heater power, 353.4 watts in both cases. The two configurations differ in 3 ways, as the table makes explicit. T01 has 1 pipe at 15 mm radius. T42 has 9 pipes at 10 mm radius each. The total heater cross-sectional area is 4 times larger in T42. And because the same total power is distributed across 4 times the area, the per-pipe volumetric source density Q_vol is reduced to 1/4. These 3 differences together produce the headline result on the next slide. Greater than 70% peak internal temperature reduction. The single pipe produces a sharply concentrated peak temperature rise of approximately 712 Kelvin with a steep radial gradient. The 9-pipe arrangement at matched total power produces a peak rise of approximately 188 Kelvin, more than 70% reduction, and a broader, more uniform heated volume. The caveat at the bottom, which I will also give you verbally, the 2 configurations also differ in total heater cross-sectional area by a factor of 4, and in per-pipe volumetric source density by a factor of 1/4. The 70% reduction therefore combines the effect of spatial distribution with the effect of reduced per-pipe source density. Disentangling the 2 effects requires a matched heater volume comparison, which is identified as future work. That said, the direction of the result, distributing the heater input reduces peak temperatures and improves volumetric uniformity, is a robust design guideline for sand storage cell engineering. This is the kind of finding that would influence hardware decisions for a commercial scale unit. Part 2. AI. Volumetric thermal prediction. We have a high-fidelity solver. It runs fast for what it is, but it is still 33 seconds per scenario. For a real-time control loop, we need something faster. So we trained deep learning surrogates, one for the 2D planar problem, one for the full 3D volumetric problem, directly on simulation data. The 2D UNet first. Trained on 42-dimensional slab geometry scenarios at 256 by 256 resolution. Mean absolute error of 0.23 Kelvin on the held-out test set. Thermal front intersection over union of 0.998. Effectively a perfect front match at our chosen threshold of half the per snapshot maximum temperature. 5 milliseconds of inference latency per sample on AV100. Maximum pointwise error of 14 Kelvin, small and localized. Top row is ground truth from the Lattice Boltzmann solver. Middle row is the U-net prediction. Bottom row is the absolute error. The three scenarios shown are T01 nominal charging, T08 discharge, and T40 the charge to relaxation transition. Notice that the error map is almost entirely dark blue. Errors are concentrated at material interfaces and are well under 10 Kelvin in most places. Good result. But 2D is a warm-up. What we really need is 3D volumetric prediction, which is the next slide. For the full 3D problem, we developed TUNet, a volumetric surrogate with several architectural adaptations, a fully three-dimensional convolutional encoder-decoder, group normalization tune for the small per GPU batch sizes we can afford at 96 cubed, an attention-augmented bottleneck that pulls global information across the volume, and a composite loss combining per voxel mean absolute error with a gradient matching term that explicitly rewards thermal front sharpness. Total parameter count, 4.1 million. Compact relative to recent 3D neural operators and 3D U-nets for physics problems. Per scenario test mean absolute error. The easiest cases are the distributed heaters, T41 at 0.68 Kelvin, T42 at 0.69 Kelvin, consistent with the smoother fields of distributed heating. The most challenging is T40, the charge to relaxation transition, at 1.08 Kelvin globally, with a localized peak error of 343 Kelvin at the temporal discontinuity when the source switches off at step 5000. That peak is a single known instant. The global mean absolute error remains sub-Kelvin across the full 10,000 step run. Overall, 0.636 Kelvin mean absolute error with 8-way test time augmentation. The best volumetric thermal surrogate we are aware of for sand storage geometries at this scale. Convergence. 11V100 GPUs using NCCL distributed data parallel with automatic mixed precision 40 epochs. Validation mean absolute error drops from 109 Kelvin at initialization to 0.71 Kelvin at convergence. Monotone after epoch 2, and the same ordering of scores reproduces across independent reruns with different random seeds. At deployment, single forward pass is under 5 milliseconds. 8-way test time augmentation is about 40 milliseconds and gives the best mean absolute error. End-to-end, we deliver over 6,600 times speedup versus direct Lattice Boltzmann simulation. The honesty callout. Our 3D benchmark uses per scenario min-max normalization computed over the full scenario trajectory, and that includes frames from the held-out test scenarios themselves. This is offline benchmark leakage. The normalization statistics for a test scenario are computed from frames that would not be observable in a real deployment setting. The 0.636 Kelvin mean absolute error is therefore an offline benchmark figure, not a deployment-ready evaluation. A retraining run with deployment-safe normalization, restricted to training set statistics only, is the top priority future work for the AI stack. Part 3. We now leave the thermal physics and AI surrogate and move to the grid. This is the longest section of the deck, 11 slides, because it contains 2 of the 3 headline numbers and the project's strongest safety claim. Let us begin with the grid digital twin itself. This is the grid model. A digital twin of a real Cypriot low-voltage feeder reconstructed from utility drawings. 308 buses for 135 line segments, 100 household-level loads, 41 PV installations grouped across 5 PV parks, and a single slack bus at the substation. We solved it with a GPU-accelerated Newton-Raphson power flow engine, developed in-house as a drop-in replacement for the Panda Power CPU backend. Across 500 random validation cases, the GPU solver reproduces the Panda Power CPU reference to approximately 4 times 10 to the minus 11 per unit in bus voltage magnitude, numerical agreement with the reference solver, not a physical validation of the feeder model itself. Mean per call cost is 10.02 milliseconds on GPU against 18.31 milliseconds on CPU, a 1.83 times speedup. That speedup matters because asynchronous reinforcement learning training calls the power flow solver millions of times, and a 1.83 times reduction per call compounds into days saved over the full training budget. The RL dispatcher itself. We use Impala with vtrace corrections, an off-policy actor-critic method that runs asynchronously on multiple environment actors and corrects the policy mismatch at the learner. The off-policy setting is deliberate. The power flow solver is expensive enough that generating trajectories asynchronously, even with correction cost, beats insisting on on-policy updates. Policy architecture, a shared linear TAN trunk with 256 hidden units, and 2 heads, a 64-way categorical policy head, and a scalar value head. The 64-way action space is the the 5 PV park disconnect mask times the 2 states of a global SAND on OFF bit. The reward is assembled per step and is shown in the gray box below. 6 weights. The line loading violation weight dominates at 50, enforcing that grid current safety is the strongest term. The curtailment and SAND value terms are the gradient signals that shape the dispatching behavior. 1 control step is 1 minute of physical time. 1 episode is 120 steps, which is 2 hours. The 60-episode evaluation split covers 5 days of aggregate simulated control time. Training is 120,000 environment steps aggregated across actors, which is about 83 days of simulated time. We evaluate on 2 benchmark scenarios, S1 and S3, differing in forecast noise level and slack tightness. 10 independent training seeds per configuration, for both the PV-only baseline and the PV plus SAND policy. Before we see the results, the safety shield that wraps the policy at deployment. 2 layers. Layer 1, the action safety shield, operates on all candidate actions and intercepts any projected to push the feeder outside the compliance band at 0.95 to 1.05 per unit, or above 100% line loading. If a candidate action would cause a violation, the shield substitutes a safe fallback. Layer 2, the SAND activation gate, is stricter and applies only to SAND-on actions. It requires bus voltages inside 0.96 to 1.04 per unit and line loadings below 95%. This protects specifically against charging-induced violations under marginal feeder conditions. Crucially, both shields are OFF during training. The agent is pushed to discover the feeder constraints from reward alone. The shields come on only at inference and evaluation. This design detail matters because of the result on slide 23, which I consider the strongest claim in the entire project. 29.9% mean winter curtailment reduction. Across 10 training seeds, the PV plus SAND policy reduces mean curtailed energy per episode from 99.36 kilowatt-hours down to 69.70 kilowatt-hours in scenario S1. The same policy diverts 22.88 kilowatt-hours per episode into thermal storage, so the curtailed energy is not just disappearing from the system, it is being captured for useful winter heating. The caveat at the bottom of the slide, verbally, the paired difference across seeds is minus 29.67 plus or minus 42.46 kilowatt-hours per episode. The reduction is economically meaningful, but seed-to-seed variance is large at 10 seeds. I will unpack this on slide 24. The headline number is real. The confidence interval deserves an honest slide of its own. 0. Across 60 evaluation episodes times 10 seeds times 2 scenarios, that is 1,200 evaluation episodes, the deterministic safety shield was never required to intervene on any action proposed by the final train policy. Think about what this means. The shield is designed to veto unsafe actions. In 1,200 episodes, the agent never proposed an unsafe action that the shield had to reject. The reinforcement learning agent internalized the feeder constraints so completely during training, even though the shield was OFF during training, that every action it proposed was already safe. This is the strongest safety claim in the project, and it is backed by evidence, not by architectural assumption. The shield exists as defense in depth, but it is not a crutch. It is not carrying the agent. The agent carried itself. For a real deployment on a real utility feeder, this is exactly the pattern you want. A learned policy that understands the physical constraints on its own, backed by a deterministic safety layer that never has to fire. Now the full statistical picture. Mean plus or minus standard deviation across 10 seeds. In S1, curtailed energy drops from 99.36 to 69.70 kilowatt-hours per episode, but with standard deviations of 34 and 46 kilowatt-hours respectively, the distributions overlap substantially. Similarly for S3. Energy diverted to SAND storage, 22.88 kilowatt-hours per episode in S1, 19.01 in S3. Violating episodes change from 0.8 to 0.9 in S1, no material change, and improve from 1.6 down to 1.2 in S3. Shield interventions on final policy, 0 in both. The paired differences, that is PV plus SAND minus PV only, computed per seed and then averaged, give us the cleanest read of the policy benefit. Minus 29.67 plus or minus 42.46 in S1, minus 16.00 plus or minus 44.50 in S3. Means in the right direction, but standard deviations larger than the mean. And this is the honest statement. Per-seed paired differences in S1 range from minus 86 kilowatt-hours per episode on the best seed to plus 22 on the worst. The mean reduction is not statistically distinguishable from 0 at n equals 10 in a standard two-sided test. This is standard behavior for policy gradient reinforcement learning at modest seed counts, and it is exactly why follow-on work includes a larger seed evaluation to tighten the confidence band. To make the aggregate numbers concrete, here is a single representative episode. This is Winter S1 test case, test_000602. The top panel shows PV generation in green and household load in black. The middle panel shows feeder scale SAND power in orange and the mean state of charge across 100 household units in blue. The bottom panel shows the bus voltage envelope over the 121-minute control steps. Episode outcome. The policy delivers 691.7 kilowatt-hours to storage with 0 violating steps. It leaves 172.5 kilowatt-hours still curtailed, and that residual curtailment is informative. The policy is not absorbing PV surplus at any cost. It accepts some curtailment when the network state does not admit further safe charging. That is correct operating behavior under a safety-shielded objective. All bus voltages remain inside the 0.95 to 1.05 per unit compliance band throughout the episode. This is the kind of dispatch pattern a real grid operator can trust. Aggressive capture of usable surplus, restraint when the network says no. Here is that episode in motion. SAND power and state of charge respond to PV surplus, while the bus voltage envelope stays inside the safety band. Here is the same episode, test_000602, run twice with identical exogenous forcing, same PV generation, same household load, same network topology, same time of day, with only the dispatch policy differing between the two panels. PV only on the left, PV plus SAND on the right. The map on the top shows the feeder state. Notice that on the PV only side, bus markers closer to the substation carry the stressed colors of the constraint palette. On the PV plus SAND side, the same buses are green. Cumulatively, the curtailment proxy falls from 28.63 megawatt-minutes under PV only to 10.35 under PV plus SAND. That is a 64% reduction on this specific episode. SAND charging goes from 0 to 41.5 megawatt-minutes, 83 minutes of active charging at 0.5 megawatt feeder scale. And the third number, which I want to spend a moment on. Peak line loading drops from 106.8% down to 98.8%. The storage-enabled policy is not just shifting the curtailment problem somewhere else on the network, it is simultaneously relieving feeder electrical stress. We were initially worried about the failure mode where you add 100 new controllable loads to a constrained feeder and just move the problem around. The side-by-side answers that worry directly. And here is the head-to-head, side-by-side. Same forcing, two policies. The PV plus SAND policy reduces curtailment and relieves line loading. Now a limitation we report transparently because it has not been solved within the project scope. Seasonal activation, measured as mean sand on steps per 2-hour episode, in winter versus summer. In scenario S1, winter activation is 2.75 steps per episode, summer 2.19, intended ordering. The policy charges more in winter than in summer. Good. In scenario S3, winter activation is 2.28 steps per episode, but summer is 5.08, more than double. The current reward and state do not impose a strong enough seasonal preference in the S3 configuration. Summer surplus in this system recovers at roughly 10% efficiency through a thermoelectric pathway, better than the 0% recovery of curtailment, but substantially worse than the 90% winter round trip of direct heating use. The policy should prefer to leave summer surplus uncaptured when winter capacity is not at risk. For paths forward, in increasing scope, add an explicit heating demand signal to the observation vector. Introduce a seasonal multiplier in the reward. Train with a seasonal curriculum. Or, for deployment, just use a rule-based override forcing standoff from May through October, which achieves the same effect with zero algorithmic overhead. All for a post-project. And here is winter against summer for the same policy. Storage activation tracks the seasonal availability of surplus PV. Before we close, a single slide consolidation of the validation chain behind this whole presentation. How does every number you have seen trace back to evidence? Step 1. Physics. For independent benchmarks on the thermal solver, Ploz wheel, thermal source 1D, cavity at RA0, cavity at RA 10 to the 4, all pass at sub% levels. Step 2. Grid. 500 validation cases comparing our GPU PowerFlow solver to the Panda Power CPU reference. Agreement to 4 times 10 to the minus 11 per unit. A 1.83 times speedup. Step 3. AI. Test set evaluation on held-out scenarios, never seen during training. 2D UNet at 0.23 Kelvin, mean absolute error. 3D TUNet at 0.636 Kelvin, mean absolute error, with the offline benchmark caveat we were upfront about on slide 17. Step 4. Reinforcement learning. 10 independent seeds per configuration. 60 episode evaluations. Match forcing side-by-side comparison against a PV-only baseline. 29.9% mean reduction in S1, 16% in S3, zero shield interventions. Every numerical claim you have heard in the last 30 minutes either traces to a physics benchmark, a held-out test set result, or a multi-seed matched baseline evaluation. Nothing in this deck was hand-waved. In summary, 3 numbers. Greater than 70% peak temperature reduction from the distributed heater design. 0.636 Kelvin mean absolute error on volumetric thermal prediction, with millisecond inference at 4 orders of magnitude speedup. And 29.9% winter PV curtailment reduction with zero shield interventions on the final policy. Future work is organized in 2 tiers. Tier 1 items are the ones that affect validity of quantitative claims and must be addressed before the method is used for quantitative design. An enthalpy-conservative reformulation of the Lattice Boltzmann solver, deployment-safe retraining of the 3D surrogate with training set-only normalization statistics, and a larger seed reinforcement learning evaluation to tighten the confidence band around the 29.9% figure. Tier 2 items are scope extensions, temperature-dependent properties and radiative transport, a matched heater volume comparison to disentangle the 1 versus 9 result, zone level or per household action granularity, a full TUNet ablation study, coupled with hotspot-aware safety shielding, and a seasonal-aware reward for the S3 summer activation behavior. The project has delivered a Technology Readiness Level 6 integrated demonstrator, 2 peer-reviewed manuscripts submitted for evaluation, and the foundations for technology readiness level 7 to 9 follow-on activities. We believe it is honest, useful, and positioned for impact in Cypriot and wider Mediterranean grid integration contexts. Funding acknowledgement. This work is part of the REALISATION-SAND-AI project, grant number ComConcept Energy /0624/0185, funded by the European Union's Recovery and Resilience Facility, Next Generation EU, and the Republic of Cyprus through the Research and Innovation Foundation, under Component 6.1 Repower EU of the Cyprus Recovery and Resilience Plan. Computations were performed on the Kyamos V100 InfiniBand cluster. Dissemination outputs. 2 peer-reviewed manuscripts have been submitted, evaluation pending, the thermal and AI paper and the grid and RL paper. This video itself is one of the dissemination outputs, and a promotional deck and online project forum are also live. Thank you for watching. I am Antonis Papadakis at Kyamos. My email is on screen. Sofia Nikolaidou, Varnavas Mikromatis, and the wider Kyamos engineering team all contributed to the work you have just seen. Thank you.